But yeah, all right. So welcome to week 4. So today we're going to be mostly honing in about 3D printing and talking about where it might be good and where some limitations lie. Um, 3D printing is a pretty amazing technology. So we're going to kind of get into it. But before that, I'm going to talk a little bit about your final projects. So if you're not aware of it, there's a final for this class, but don't worry, it's not that bad. Um, you know, Basically up here is the list of requirements for it. So it's pretty loose. It's basically giving you a blank canvas, allowing you to design whatever you want, school appropriate, of course. Um, just as long as it's not something that we've already made in class, which is like pretty self-explanatory, you can basically make it. The main requirement is that we want at least 5 design features. So a design feature would count as something like an extrude or like a cut or a fillet. So you'll probably come to realize pretty quickly that 5 design features is really not that bad. And they don't have to be like 5 unique ones. So, you could have like several extrusions and stuff like that, and that would count as more than one. But again, these are pretty like relaxed like parameters for a final project. But we encourage you to, get creative. A lot of people usually use more than 5 design features, and they'll make something pretty cool. I forgot the finals in my car from last session, but um, if you ever like pass them while like coming into class, some of them are pretty cool. Um, the last thing is design for manufacturability. So again, all these finals are 3D printed. So I'm gonna encourage you to design it to be 3D printed. So people have given me designs in the past that are very not 3D printer friendly. So when I go to print it, it either would fail and I wouldn't be able to make it for them, or it'd be super fragile that when I give it to them, it like basically disintegrates in their hand. So I'd prefer that not to happen because that's just kind of not very satisfying to see like 5 weeks of work just like blow up in your hand. So if we can avoid that, that'd be great. So hello. Um, I'll tell you some tips today that might be helpful when designing your stuff. So yeah, again, these are some final projects from past sessions. You've probably seen these photos. I've used them like extensively, but it's pretty obvious here that these have more than 5 design features. So you can definitely like go pretty crazy and make these things. But if you're like scrapped for time or you got exams and stuff, I totally understand. You can make something a little bit more simple. But yeah, this is the kind of stuff that is possible in this class. So yeah, keep that in mind. But yeah, so we're gonna go into designing for manufacturability. Um, Basically, there's a bunch of different ways that you can go and make stuff. There's many processes, but they usually fall into 2 different categories. The first one is what we would call subtractive manufacturing, where you usually take a piece of raw stock and then you cut away at it with some tool uh, until you eventually have some final product. So you see on the left of the PowerPoint slide, there's like this block and then this tool comes in and cuts away at it, and then you get this like profile, right? So subtractive manufacturing is pretty great. You can use a ton of different materials. Parts can be pretty strong, but it's typically a little bit more expensive, right? Because you're generating a lot of waste from like cutting away at a material. Usually the material cost is higher, along with like any amount of labor involved. Like CNC machining can get pretty expensive, so um, you know that's kind of like a financial limitation to a lot of us, at least for me. But they're pretty great. You'll see it a lot in industry, especially for like metal components. But here's just like a couple of processes that are subtractive. So stuff like drilling holes and stuff is subtractive, obviously, because you're cutting away a hole in something. But it can get more complex with stuff like milling and turning, where you'll have a tool that can cut away and make complex profiles, which is pretty cool. Or you turn the part and then use another tool, like a more static tool, to make that complex part. Other stuff like grinding and routing is also kind of a subtractive process. So these are all kind of different processes that you might be thinking about. Um, so yeah, these exist. They're pretty great, but because they're expensive, I'm not really going to be talking a lot about them today. But if you do design for certain processes, or if you're designing a part, you might want to think about the process at which you want this part to be made, because they have different limitations. So yeah. The other kind of manufacturing process is additive manufacturing. So in this example, you can see that it kind of starts from nothing, but then we have some kind of nozzle that deposits a material, which eventually becomes the product that we're looking for. So we're mostly going to be talking about this today, mostly 3D printing, but that's just kind of the basics of additive manufacturing. So like I said, 3D printing is definitely one of the processes we typically think about when we're talking about additive manufacturing. But there are other processes like injection molding that is also technically additive. So yeah, it's pretty cool. It's pretty nice because the amount of waste this kind of process uh, kind of generates is usually not as high as a subtractive process, because you usually have some kind of mold or some machine that can make it without using a lot of excess material. So it can typically become a little bit more affordable, especially with 3D printing, which I'll just start getting into now. So 3D printing obviously has a bunch of different applications. We're seeing it more and more in like really big industries, especially stuff like aerospace and stuff like that. You'll see like parts that are like 3D printed for like airplane wings or like rocket ships. And the big advantage to 3D printing is that you can get a lot of complex geometry without a lot of work. So it's really advantageous when making stuff. You can make really organic looking things. This photo here is like an organically generated like control arm assembly for like a car. It's like a supercar company called Zinger, if you didn't know. But like their whole like suspension geometry is like designed with 3D printing in mind. So you can see all of these have like crazy organic lattice structure looking things that would be like wow, I can't talk, ludicrously expensive if you were to manufacture that like with a subtractive process. So 3D printing is really great for this, really great for like highly optimized things, but also for rapid prototyping. A lot of the advantages of 3D printing comes from the fact that you don't need expensive tooling to make your part. So you can have a 3D printer and you can make a bunch of different shaped objects without it costing very much. So yeah, there's also other more niche applications like clothing and jewelry, and even like food. So people like to 3D print like chocolate and stuff. It's kind of funny. But yeah, there's a bunch of applications. With that comes different kinds of 3D printing. These two are a little bit less common, but I was just going to go over them first. SLS or SLM is basically a process where they take a metal powder or just some kind of powder. Usually it's like a nylon powder or like a metal powder, and then they'll use a laser and they'll like melt a tiny patch, and then they'll cover that patch, and then they'll melt more stuff on top of it with that laser. So again, you're kind of stacking materials until you get your final product. So that's what SLS or SLM does. You can get pretty like strong parts. They're really nice, but unfortunately they're a little bit more expensive. So they're not really like desktop friendly yet. The more desktop friendly version of it would be something like an SLA printer, where instead of using a powder, it uses like a liquid resin. and underneath it has basically a display, almost like a TV that shines UV light, and then the resin cures with UV light. So they'll shine a profile of whatever thing they're printing. It'll move up a little bit and then it'll shine it again, and then it'll do that over and over again until you have your part. So that's just kind of like a theme of 3D printing. You know, they kind of does it in layers. So yeah, these two are pretty cool. SLA is like something that you can get for the desktop, but it's typically a little bit more messy just because you have to cure stuff. So we're not really going to be talking about that much today, but these do exist if you're like interested in them. So the main thing that we're going to be talking about is FDM or FFF 3D printing. And basically you use a spool of filament or a material that is deposited through a nozzle. So basically the way I like to describe it is it's like a very fancy hot glue gun, but instead of hot glue, it's plastic. And then instead of you pulling the trigger, you connect it to a robot and then it does it for you. So basically the basic principle is you have some material that feeds through a nozzle, and then the computer will control it and like precisely deposit the material where it needs to be. So I'm sure most of you have kind of heard what 3D printing is, but you know, that's pretty much the basics of how it works. Okay, so now we're going to be going into the settings for 3D printing. Basically, when you 3D print things, there's an insane amount of settings for you to choose from. If you think of like a 2D like printer, you might be able to choose things like DPI or stuff like that for like resolution. But because you're working in 3D space, there's so much more for you to change. So the first thing that you might want to keep in mind is the layer height, and that's basically how thick each layer of the print is. A lot of these words are kind of self-explanatory, but basically, if you see on the left, the layer height is very coarse or very tall, so it's like 0.8 millimeters for every layer, and then the right side is a lot thinner at like 0.1. And there's different advantages to both. Again, a lot of these settings are going to be based on what you're trying to achieve. But with a really high, like a really tall layer height, you're going to be achieving faster prints, mostly just because there's less movement for your machine to go through. And so less layers usually means less time. So you get a lot of speed, or you'll get a faster print, but you know, you're going to be suffering some resolution. So I usually think of the layer height almost as like the DPI of like the 3D space. So if you have a really fine layer height at like 0.1, the print will take a lot longer. But if you're printing something that needs to be highly detailed, that might be something that you want. Another thing about layer heights is typically 3D prints do fail on the layer lines. So when you print with stuff with a bunch of layers, there are more points of failure. So technically speaking, a print with like a larger layer height at like 0.8 is a little bit stronger just because there's less points of failure. You know, your mileage may vary, but that is something to keep in mind. For mechanical components, you might want to increase that layer height a little bit. But yeah, that's layer height. The next thing is perimeters. It's basically how thick the wall of your 3D print is. If you didn't know, a lot of components that are 3D printed are hollow. So the inside is, you know, it's not solid. And it's partially like a time and material saving measure, but it's also just because a lot of that material is unnecessary for most applications. A lot of the strength from your components usually comes from the outside, so any amount of material on the inside in like a traditionally manufactured process sometimes is unnecessary. So to maintain strength, you have to, you know, make sure you have enough perimeters, because if your perimeter is really thin, it'll be, you know, really thin and potentially flexible. But if you add more layers on the outside, you'll be creating a stronger part. The next slide will talk about infill, but mixing and matching the number of perimeters with the infill can generally give you a good amount of strength in your part. Personally, for me, I think adding perimeters is would increase your strength more than just bumping up your infill by a lot. Obviously, you need like a good balance of both, but perimeters usually are a little bit more effective, especially for the amount of like material that it uses and the time that it uses, or the time it takes to print it. So if I wanted a part that wanted to be stronger and the default was like 3 perimeters at like 15% infill, I would probably choose like 4 perimeters and 15% infill over 3 perimeters and like 20% infill, if that makes sense. But again, this kind of depends on application. Obviously, if you increase the number of perimeters, it takes the machine longer to print just because there's more paths for it to take. So keep that in mind. But generally, more perimeters means it's stronger. It'll just take a little bit longer. Infill, like I just mentioned, is basically how dense the part is on the inside of the perimeter. Again, most prints are hollow, so choosing your infill percentage is usually a little bit important. Typically, for most prints, it's usually like 15 to 20%. But if you want stuff stronger, you can bump this infill percentage up a little bit. Again, I think it's more effective to add perimeters, but you still want to have a little bit of infill, just because having it completely hollow would probably compromise some of its strength. But yeah, obviously, if you increase the infill, you're adding material cost, but you're also getting some strength. So this is all drawbacks that you might want to keep in mind. Onto some limitations about 3D printing. Because we're limited by the laws of physics, most FDM processes are limited in the sense that you can't print things in midair. And so to do that, if our model calls for something like that, we'll use something called supports, which is just like a sacrificial material for you to print on top of, for you to remove later. So you can see here, this like model has this cylinder kind of going out sideways. If you tried to print that normally without supports, it'll just droop and then the print will fail because there's nothing to support it on either side. So to make this like manufacturable in the slicer, which we'll be working with in a little bit, you can generate support material to kind of make sure that the part doesn't droop. Obviously, you remove this after you print it so you can get your geometry that you're looking for. So yeah, it's pretty nice. But as the designer, you can try to design the need for supports out. Obviously, there are some scenarios where you have to use it because if you designed it this way and the geometry has to be like this, you have to use supports. But if you maybe design something that didn't need it, you can kind of limit the amount of waste material because obviously the sacrificial material has to be removed and it's just like trash after that. Also, printing with supports adds an extra step in the process because you have to remove it afterwards. So if you're printing like a bunch of pieces that require supports, it's gonna take a little bit more time to print it. It's gonna cost more. But then it's also just going to be a pain because you have to get someone to remove it or you have to do it yourself. So typically when I design stuff, I try to avoid supports as much as possible. But it is an option if you ever need it. But yeah, here's a good example of supports. You can see here like this H, it may not have needed it. I'll talk about bridging in a little bit, but you can see here in its orientation, this person decided to print it with supports. This T would probably need supports just because it's sticking outwards with nothing to support it. But okay, what do you think the person printing this could have done to avoid like printing supports? I'll leave this as like an open-ended question. if anyone wants to answer. Yeah, that would work. Does anyone else have? Exactly. Yeah. So those are like two good options. Um, making sure like you're designing your part to be printed in a certain orientation can be, something that you should be thinking about. Because if you design it in a certain way, you can avoid, or if you design it to be printed in a certain way, you can avoid needing supports. Um, Also, this is a little bit more like nitty gritty, but depending on the way you print it, um, you can make a part like stronger or weaker. So depending on like the forces your part might be subjected to, if the forces are along the layer lines, your part is more likely to break. So I don't know, let's say like this can is 3D printed, and I printed it like this. And I don't know, let's say this was a bolt, right? If I like screwed it into something and then the layer lines are like this, the part's inherently going to be weaker because the prints are weak along the layer lines. So if I like for some reason like tighten this a bunch, then like it would snap like on a layer line. But if I printed it like sideways like this, the layer lines are like opposite from the direction of the force that you're applying to it. So your part is going to be stronger. So if you printed like a bolt sideways, it's like typically going to be stronger than if you print a bolt like facing up, if that makes sense. Um, yeah, this is like kind of technical, but this is the kind of things that I think about when designing like mechanical components for 3D printing. Okay, so with that ramble out of the way, we're gonna just start slicing components. This is gonna be your assignment, your main assignment for today. So we're gonna download a software called Prusa Slicer, and then running through this might give you a little bit of a better idea of how printers work. But yeah, basically there's a bunch of different softwares out there that will convert your model into something called G-code. G-code is basically a really long set of instructions for your 3D printer to follow to make your part, right? So you can't just like send your printer like your Fusion file and it'll make it for you. You need to use a software called a slicer to convert it into a bunch of movement commands for it to follow. So today we're going to be using Prusa Slicer, but there's a bunch of them out there. A lot of people like Cura and like Bamboo Studio, and personally I use Orca Slicer now, which is very similar to Prusa Slicer. But yeah, if you go under the Resources tab, there's this link here, and then it should take you to the Prusa Slicer website where you can download the software. And yeah, we can just get that going. The download's usually pretty quick compared to Fusion, so yeah. Is anyone having trouble getting to this website and downloading it? Well, my Prusa Slicer is like one version out of date, but it should be pretty accurate or pretty similar. I don't think the UI changed that much. I'm just gonna walk. Okay. Who's still downloading Prusa Slicer? Okay, all of you are done. That's sweet. Okay. Once this loads, I will get into it. Okay, so when you first download Prusa Slicer, it'll probably open into this wizard. It'll give you the option to like log in if you press next with like a printables account or Prusa account. You can kind of skip that if you don't have one. It's not a big deal. But if you go down to Prusa Research, it'll allow you to select printers. So here are like all the printers that Prusa makes. This is basically the company that kind of made this software, but they also make hardware. This slicer isn't exclusive to these printers, especially because it's open source. There's a bunch of other options. If you go under here, you can see there's a bunch of like other manufacturers that you could get presets from. But today we're just going to be selecting one of these Prusa printers. For today, let's just select this Mark 4S with the high flow 0.4 millimeter nozzle. So you want to select this one. Should be under like this core one, and it should be like HF 0.4 millimeter, or it might just say 0.4. But yeah, pick this one. And then you just press finish. The rest of them are, well, actually, you should probably also add a filament. So select this printer. Is anyone having trouble finding this printer? Sometimes people exit out. Oh, okay. If you accidentally like exit out of this and you're kind of in this window and you didn't add the printer, you can click on like this printer tab over here and then do add or remove printers and then add or remove presets. Okay, yeah. Sometimes it takes like a hot minute to reload those, so don't worry if it takes a minute. But yeah, I'm asking you to use this printer specifically just because like it's going to keep everything consistent with the times and stuff like that because different printers have different like speed capabilities. So making sure you pick the right printer will ensure that the time is the same. So yeah, pick the high flow 0.4 millimeter nozzle on the Mark 4S. And then we can just skip all of this and just go down to filaments. And then I think let's just select like generic PETG. So I went under all PETG and then I found generic and then like generic PETG is an option. You can just click on that checkbox, just make sure it's something that you can select. And then you just press finish. You'll probably see that I have a bunch of presets and it's because I have a bunch of different printers. So this for you is probably going to be a lot smaller, but yeah. So it should auto select it for you, but if it didn't, you can go under the printer tab and find the printer that we just selected, which in this case should be this one, Mark IV input shaper, I believe. I'm going to double check. HF. Hello. Oh, thank you. I forgot about it. You didn't have to get it though. Thank you. did. I didn't see. Okay, so I forgot this earlier, but if you desire, feel free to come up and grab a benchy. We're going to be slicing these in a little bit, but it's a pretty cool little model. Also pass around like a couple like unfinished ones I have just so you can see a lot of these are hollow and stuff, so it's pretty cool. I'll just pass this around. Yeah, you can take these benches home. Like a craft kind of one. So if you just want it for free, please take them. Some of them are better than others, but I'll explain that in a little bit. Okay, so I'm under the assumption that you've got this Mark 4S. Yeah, what's up? Under filament, you should select generic PETG. So I'll do that now. So you should have, this here under like the high flow 0.4 millimeter. And then for speed, or not speed, for filament, do generic PETG. Just because different filaments sometimes have like different settings on minimum layer times and stuff like that. So we're just gonna try to keep everything consistent so everyone's time is the same as mine, or at least like really close to mine. Okay, raise your hand if you need help getting here. Okay, no problem. The top ones are like kind of bad, but they're better if it's, yeah. My extruder was really messed up when I was printing those, but I fixed it. I did. Okay. So now that we have, our slicer and kind of printer set up in our slicing environment, we're going to download a model to slice. So the model of choice today will be the 3D Benchy. It's a very popular like calibration model, which I'll kind of go over in a little bit. But we can just kind of Google this and then find the Benchy. So if I could spell right. So there's like a website for the Benchy, but then there's a bunch of websites that it'll route you to download from. Thingiverse is like a pretty popular website there. Um, it's like it's similar to the repositories that we were talking about last week, like GrabCAD and stuff, but these are specifically for 3D printing. So Thingiverse is one of them. Printables is another. I primarily use Printables. It's another like Prusa software kind of thing, but there's a bunch of them out there. So yeah. Under files, at least here in Thingiverse, you can download the Benchy. We just want to download the full thing. So we're going to kind of download the top one. It should be an STL file. But then the other ones are just like specific sections of it. But we're just going to download the full Benchy. So once we download it, we can insert it into this slicing environment. You can drag and drop from like your file explorer, or you can do, Control or Command I if it wants to load. Okay. So you're going to insert it into the slicing environment. and then it'll kind of display this printer or this model. You can see we zoom in and like rotate around. It's a nice and smooth model. Oh yeah, I should probably tell you how to move around. So if you want to like spin around, you hold the left click. It's a little bit different from Fusion, but the zooming is the same. You can zoom in and out. But then to pan side to side, you kind of right click and hold it. So yeah, that's just usually the navigation for this kind of stuff. But we have this 3D Benchy right here. Once we have the part that we want to print, we can start specifying different settings, right? Obviously, you can change these settings at any time, but you'll have to recalculate or reslice the model before printing anytime you make some kind of change. So let's go back to here. Oh, what happened? Okay. So we're just going to start populating these different settings here. So the first thing I'm going to change is the number of perimeters, or actually I'll start with the layer height. So there's a couple of ways you can go about changing these settings. A lot of the like high level settings are found on the right side up here. So under print settings, this is where you can specify your layer height. For this assignment, we ask you that to set it to 0.15 millimeter speed. So there's like a structural one and a speed profile, but we're just gonna leave it at speed. So 0.15 millimeter speed. For reference, I typically print at 0.2 millimeters, but I'm having you change it just so you know how to go through the interface. But yeah, we're gonna set it at that. For infill, we're requesting 20%. So over here, we can set this to 20 right here. And then we're changing the perimeters, and then we're adding supports. So not all of the settings can be found here. So if you ever need to be a little bit more specific in what you want to change, you can go under the print settings tab here and kind of like the top left. And then you'll get more parameters that you can change. So up here is the layer height, just like we had before. But you can also change things like the perimeters. In this case, we want, I believe, 3. So we change this from 2 to 3. There's some more settings, but we're just going to leave it for now. If you ever wanted to change the infill another way, you can go under the infill tab and change it here. You can even change like the pattern at which it does the infill, but we're going to leave it as grid just so all the ones are the same. But if you want to mess with that like later, you can change it and then you can see like how it affects the model. So the last thing is turning supports on. Over here, you can enable supports with this like generate support material, and then it'll do auto-generated. The other way you can enable it is by going back to your platter and then enabling supports here. For this, just set it to everywhere. I will say that when you print a Benchy, you usually don't have supports on, but I'm just having you turn the supports on for this assignment so you know how to do it. But yeah, we have the filament already, and then the printers, obviously the printer we selected. So with that, we can press slice down here, and then the computer will generate a toolpath. Or it's going to be slow. It's usually not this slow. I guess it's about time for me to restart my computer. Okay, so once it finishes slicing, you'll see here there's this benchy and there's a bunch of stuff on it. That kind of green stuff is all the support material that you just enabled. But there's some important information here down at the bottom. It'll tell you like how much filament you're using, along with how much time it's going to take. So if you did everything right, you should have it at about like an hour and 19 minutes. I think sometimes on Mac it goes to like an hour and 20 minutes, but as long as you're within like a minute or two, you should be good. Raise your hand if you're not here, which is okay. Okay. So if we look at the model, it'll kind of just give us a better visual representation of what all of these settings do. So the first thing is the layer height. So if you look here on this slider over here, it says there's going to be 509 layers, and the maximum height is like 48.05 millimeters, right? And if we change this slider, you can see kind of how the printer works. So if we go all the way down to the bottom, we see there's like this one 2D profile. We can change this slider to show like the process on each layer. The arrow is like the nozzle of the printer. You can see how it fills in this area. The green is the support, and then it starts filling in the model, right? So this is a cool representation of what it does. So it'll do that for that layer. It'll go up 0.5 millimeters. Oops, I added a pause. Okay. So it'll go up 0.5, and you'll see here like it stacks another like profile on top of it, and then it'll continue to do that over and over again until you have your finished product. So this is a kind of a easier way to kind of see what the printer does. But now we can start changing settings. Obviously, like you should have this as your you know, your final time should be this, but I'm going to start changing stuff so you can kind of see like the differences that it makes. One thing about, I'd say, the top of this benchy, you can kind of see if we go back to like before we sliced it, this top is like a smooth surface, right? But it's, if you look at it closely, it's actually like, it's kind of angled on the top, but it looks smooth on the, you know, on the model, but when we slice it, you can kind of see there's almost like this stair stepping effect, and it's because it prints it layer by layer. So you can't always get a smooth surface, especially when it's like slightly angled like this. So that's kind of a limitation, something to keep in mind. It's usually not that big of a deal, but if surface finish is like important to you, you might want to change, you know, the orientation, right? Obviously, like the surface finish on the side of the hull is going to be pretty smooth, but then here on the top, it's a little bit stair-steppy. You can make this like better or worse by changing the layer height. So if we increase the layer height to something like 0.28, you're going to see this stair-stepping effect is going to get worse. So I'm going to change this. I'm going to transfer all these settings just because I can. And when I slice it, slow computer. Okay. Okay. Yeah, so when I slice it, you can see here that this stair-stepping effect has gotten worse, right? There's less steps, I guess, but each step is taller, if that makes sense. Um, you can also see that the layer height or the printing time went down significantly, right? So like I was saying before, if you increase your layer height, you're going to get much faster print times just because there's less layers, right? There's only 190 for this one. The other one was, what was it? I forget, like I think it was close to like 500 or something. I forget what the number was. But you can see here, there's only 190 layers, right? So that just means there's less movement for the printer to do, and it can usually print your model faster. So yeah, you can also, change other settings. You download the Benchy from the internet. So just go to like Google and type in 3D Benchy, and then you can go to like the Thingiverse and then download like the full STL right here. But yeah, if I was to change another setting, I'll do infill next. So here you can see like infill here looks about this dense. But if I were to change it to something a lot higher, like 70% for whatever reason, you can see how the model changes. Every time you do make a change, you have to reslice it because it has to recalculate the path for the printer to follow. But you can see here when you increase the infill, it makes the part more dense on the inside, right? When you go all the way to 100, your print is just going to be completely solid. If we change the number of perimeters, I'll just change this to like some really large number so you can see. If I reslice it, the walls are going to get thicker, right? Again, depending on your use case, these settings might be something to keep in mind. But yeah, you can see here like this hull is like pretty thick and it's going to be a lot stronger than before. So yeah, you can also see that the print time is starting to increase when we increase these numbers. So again, it's kind of a balancing act between the strength of your part, the amount of money you want your material or you want to use in material, along with the time that you have. So yeah. Again, typically people print at like 3 perimeters and like 15% infill for most like non-structural components. But when I want something a little bit stronger, I usually go like 4 perimeters, like 25%. So like most of this printed behind me is like 4 perimeters, 25%. We can mess with it in a little bit. But it is 3D printed? Yes, I'll talk about it a little bit later, because it's like not, Anyways, I'll talk about it in a bit. But yeah, that's basically how the slicer works. It's a lot of these settings are very dependent on your use case, so keep these things in mind when you're slicing stuff. I'll be talking a lot about materials and stuff like that next week, but I also want to go into some of the limitations. So I talked a little bit about the limitations earlier. My computer's going to die. Give me a second. But this is kind of the part that I hope that you pay attention to, because this might be relevant to whatever you design for your finals. So yeah. Again, like I was saying, a lot of this has to do with the fact that printers are subject to the laws of physics, especially gravity. So a lot of prints will have something called overhangs, and it's the fact that sometimes your model will have some geometry that will go outwards from the part underneath it. So in this case, you can see here this angle is not super aggressive, so the printer can typically recreate it pretty easily. But as you go more and more extreme on these angles, it'll become harder for printers to reproduce it. Typically, I like to keep it safe and just lock or try to limit most geometries to not overhang by more than 45 degrees. Um, Part of it is just kind of like a visual thing. Like I like things, at nice like 45-degree angles. It usually looks pretty good. But it's also just a little bit less stress on 3D printers. I'd say most modern printers can usually go up to like 60 degrees, but depending on your hardware setup, you might want to keep this overhang percentage in mind or like angle in mind. Um, so yeah, most designers usually just kind of design for 45 degrees, but on certain geometries, if you really need it to be more, most printers can do it. But once you get closer to like 70 to 80 degrees, it becomes pretty difficult for the printer to reproduce. So you have like insane cooling. So anything over like that limit, you would usually have to enable some kind of support material to make sure that part is, supported on its way up. So I recommend 45 degrees just because it's usually pretty simple. A lot of this can be achieved with like a chamfer, right? So if you have um, like a piece here and another piece that extends outwards, you can add just a chamfer on the bottom to make a nice smooth transition from like one geometry to the other. That means no supports. It makes the print easy to reproduce. So yeah, I'm gonna hide the supports here. Actually, I can just do this. So the reason why the benchy is often used as um, like people call it like a torture test or like a calibration print is because the benchy has a bunch of features on it that are difficult or that can be difficult to reproduce, right? And one of these are overhangs, right? So if you see here, like the angle of this overhang on the hull is a little bit more than 45 degrees. So, if you have like bad cooling or your printer can't do overhangs very well, it will show up in a 3D benchy, right? If you have bad overhang performance, this hull won't come out clean and it'll look kind of like droopy and stuff. So printing a benchy can give you a good indication of what your printer's limits are. So if you have like bad overhang performance, this will look ugly, and you'll know that you either might need to increase the cooling or you just need to print stuff that aren't at extreme overhangs, right? Other sources of overhangs are like this arch here on the little cab um, of the boat. You can see here as the print progresses, if you think about like the tangent line on the circle, it becomes like progressively more and more like to 90 degrees, right? The top of this hole is just like flat technically, right? So if you have, bad overhang performance, like these will also droop. So that's one reason why we use the benchy here. So that's overhangs. Try to keep it under 45 degrees if possible. Like I said earlier, vertical holes can be perceived as, or vertical holes are technically overhangs. So like holes or arches, um, you know, have that overhang, especially when you get to like larger diameter holes, those overhangs can become more of a problem. For smaller holes, usually like your printer is good enough that it can kind of compensate. But when it gets larger and larger, you're going to have large areas with really extreme overhangs, and your printer's not going to like that. So typically, you might want to enable supports for these vertical holes. Or if they're small, you can just kind of let it go, and then sometimes the top will droop a little bit, but it'll be like close enough. One way to combat this is by designing the overhang out, right? So again, we have the power to eliminate the need for supports by just designing things in a certain way. One way I avoid like the overhangs on vertical holes like this is by changing the hole into more like a teardrop shape, So if you think of this teardrop, the two lines that come off of this hole, I typically set at like a 45-degree angle, right? So again, we're going back to here. This 45-degree angle is nice and easy for the printer to reproduce, so we won't have any drooping here. So typically, I would just add two lines that are perpendicular to each other, and then I'll have the ends of the line, or I'll have the lines be tangent to the circle, right? So again, we're using these geometric, the geometric constraints to, add more functionality to our parts. So this teardrop is pretty cool. I like to use it a lot. Some people don't, but this is one use case that you might find useful. Bridging is another concern. So again, when we go back to supports, we can't print things in midair, but some printers, especially those with good cooling, can do like short spans of areas where there's nothing underneath it, right? But this requires like having two different places for it to bridge across, right? If it's just like cut in the middle and it just prints in midair, like it's not going to work. But if there's another place to kind of like stick the other end of the filament to, you can kind of bridge across. Depending on your printer's capabilities, you might be able to bridge longer or shorter, but typically the longer the bridge gets, the more sagging you're going to get. So you can see here, like on the bottom with a short bridge, it's not drooping that much, but then as you go longer and longer, you can see the filament is sagging a lot. So depending on, your model, you might want to enable supports for a bridge this long. But if it's a short bridge, sometimes printers can reproduce it pretty well. If we go to the Benchy, like a good example of a bridge would be like this top of the window here. You can see it's a straight shot from one side to the other. It's a bridge. And if your printer has good cooling, then it won't droop that much. So let's see. This one's like bad, this one's like better. Okay, let's see if I can turn the document. I've never tried this before. Watch this not work. Power this on. Okay, give it a second. Okay, cool. So these are both benches. It's not super in focus, but you can see here the one on the right, like my cooling was not high enough, and you can see here it was drooping like a ton. Partially it was because this filament was really wet, so you'll see a bunch of stringing too. But you can see here like this bridging performance is terrible. But here on like this benchy, you can see this bridge is like almost flat, right? It's because like this printer that I have, the cooling is pretty adequate, so it can create really clean bridges. Obviously, if this bridge gets longer and longer, it's going to get more difficult for the printer to reproduce. But if possible, avoiding like these long bridges by designing them out would be great. If not, you might get something like this, and it can get kind of ugly unless you enable supports. So that's a nice example there. I should keep this bad benchy for demonstration purposes. But yeah, please or try to avoid long bridges unless like your model really calls for it. There was a session in the past where I said, please don't do long bridges, and then someone sent me a model of the Golden Gate Bridge. So they probably weren't really paying attention because they basically gave me an extremely long bridge, and the model was super thin, so it was like basically impossible to print. And I handed it to them, and then they like broke it instantly, and they were sad, and I was sad too. So please don't do that because again, I want you to have a really cool final product or final model for you to like actually, enjoy having on your desk or wherever you put it. So yeah, keep this kind of stuff in mind. The next thing is kind of a little bit more technical, but 3D printing is subject to a lot of thermal expansion, just because when you melt a material, it'll expand, and when it cools down, it shrinks, right? Um, this can become a problem more so with certain materials. It's usually less of a problem now just because printers have gotten better. But sometimes you'll have like warping and stuff like that. I don't know if I have an example with me today, but if you have a print that sometimes really thin parts that are really long tend to like curl, and then like curl up on the corners like this. So mhm, mhm. Yeah. Yeah, so that's a good example. The next slide has another pretty cool example. But you want to account for this when you design stuff. So as much as I wish that they were perfect, 3D printers are definitely not perfect. I'd say the tolerance is usually within like zero point 0.2 to zero point 0.4 millimeters. If you have a well-tuned printer, it can be a little bit smaller. But again, the whatever you design in CAD, the dimensions will be probably slightly different from like your printed model. Um, so if you print like a 20 millimeter cube, it might be like 20.1 like wide, or like 20.2, or even like 19.9, right? So depending on like the fit that you want, you might want to print like calibration tests on your printer to see how much things expand or contract. Um, and you should probably be adding tolerances into your models if you want things to fit together, right? Again, when you CAD stuff, like Fusion 360 does not care about physical limitations. So you can have things like phasing through each other and it won't care, right? But when you try to assemble something that had like zero tolerance in Fusion, you'll probably be having a hard time. So this is a case from one of the past sessions. Someone created this Lego-like figure, but they didn't add enough tolerance for the torso and the body, right? So it could have been like zero tolerance. So when we printed it, um, the kind of pegs that go into the torso were too large, or the holes in the body was too small, right? And because of that, when we tried to put it together, it didn't fit, right? So if you have multiple parts that you're designing for, you might want to add a little bit of clearance or tolerance if they're going to be fitting together. Um, Typically, I like to add like 0.2 millimeters for holes. So if I have like a bolt that I'm putting through, like I use a lot of M3 bolts. So if I want the bolt to slide through nicely, I add 0.2 millimeters. So I'll be like, this hole is like 3.2 millimeters. So I can just slide a bolt through it and, it'll go through with no problem. But again, I added that extra tolerance to give it some leeway. Um, Not really. So when you like design stuff, I mean, I guess you could scale everything by like a percentage. But typically what I do is I specify the tolerance for like the feature that I'm doing, right? So like the outside might be like catted to an exact dimension, but then like for holes and stuff, I'll make them like oversized or undersized depending on what I'm doing. Yeah. Um, the other thing about this is like elephant's foot. So basically, when 3D printers like print onto the bed, sometimes the offset from the nozzle to the bed isn't quite calibrated super precisely, or sometimes the layer height is just set a little bit too low. And if the nozzle is a bit too low on the first layer, the bottom layers can kind of squish out a little bit. And depending on your model, if you need this wall to be exact, that may not be desirable. Um, I don't know if I have a good example here. These are all okay. can kind of feel it. So I'll pass this model around. If you run your finger down like the base of the part, you can kind of feel that the edge, the bottom edge is kind of squished outwards a little bit. And that's what we call elephant foot. So this typically happens, um, again, when the Z offset isn't precise, but there's ways to combat this. One of the big things I like to do is I like chamfering all the bottom edges of my prints. So, I might chamfer it by like 0.4, 0.5 millimeters. So in Fusion, like the bottom is a little bit undercut, but any amount of like elephant's foot that might come from this bottom will be or should be like underneath um, like the normal surface, right? So if I was to like chamfer this bottom edge a little bit, when I print it, even if it squishes out, there's still some amount of tolerance, so it'll still be kind of smooth on the bottom, if that makes sense. Again, these are all like really nitty gritty things that you kind of pick up with experience. So, I hope you keep these in mind, but they're not always relevant to your application. But yeah. With that said, there is a quiz today, but don't freak out because you have like infinite attempts. So this is basically, again, just kind of running you through like some of my 3D printing philosophy. So if you take the quiz, I think it's like 32 points. I think it'll tell you like which ones are right and wrong. But again, this quiz is mostly for your knowledge. It's not because like I'm trying to scare you. So yeah, please feel free to take the quiz now. But that's basically it for today. But yeah. Also, if you want, feel free to take a Benchy because I print way too many of them and I don't know what to do with them. So if you want one for your reference, please take one. Also, if you want to wait a little bit, we can mess with that, but not right now. To change the layer height, you just go under print settings and then change it here. It should be on the top right. Yeah, 0.15 speed. Does anyone have any questions about 3D printing? No? Okay. If you have any questions about like if your final model is like printable, um, feel free to like reach out to me and like send me a photo or something and I can give you like recommendations. Um, oh, one thing I didn't really mention, like minimum sizes for stuff. For most like important geometries, I wouldn't make them smaller than like 2 millimeters. Just because anything smaller is probably gonna break. If you're making like a cone, obviously like the top of the cone is gonna be smaller than 2 millimeters. But if you're making like a wall or something like that, I wouldn't make it smaller than 2 millimeters. People will send me things and they're like super, super skinny. Like people will send me like flowers and stuff, and like the model itself is like amazing, right? They spent a lot of time making the petals, but I feel bad because when I go to print it, the model is so thin that like when I take it off the build plate, it might like break. So keep in mind when you're designing stuff like that, because if you make things too thin, it might break. Um, for the size of stuff, I'll just say like please keep it somewhat reasonable. It's kind of hard for me to give you like a concrete like size for you to adhere to because some people like really tall and small things, and then some people print like really wide things, but like they're pretty short. So just like keep it reasonable. My printer can print like 300 by 300 by like 250 millimeters, but please don't send me something that big. Like that is gonna take me like over a day, and I'm gonna be spending a lot of material printing that. So maybe something like around the size of your hand, like desktop toy kind of size, is preferred for your final project. If you need something bigger or if you're like curious, please just ask me. Sometimes people will like print design things at like a really small scale on accident and they'll send it to me and I'll scale it up, or they'll make it really big and I'll scale it down. But if you have like a reason to need like exact dimensions, like I think someone made like a toothbrush holder, and it has to fit the toothbrush. So if I like scaled it up and down, then it like just would be useless. So if you have like specific requirements, please just let me know. But if not, I might scale things like to my discretion, if I think that like the model is too big or small. So yeah, feel free to reach out if you have questions, but please keep it reasonable. Again, I think there's like 50 of you, so I'm going to be printing like 50 final projects. So please keep that in mind because I would like to get them to you before the semester ends. So if you send it to me soon, when you turn in your finals, then I can get printed. So yeah. But yeah, with that, we're ending pretty early today, so feel free to leave. If you want to stick around and play with this, then we can do that. I'll bring more of them next week. I just like forgot. But yeah, if you would like to stick around for it, feel free to do so. But yeah, I'll see you next week. Also, next week, we will have a printer demo. So I'm going to bring in a 3D printer next week. So if you want to see one in action, please come by. I'll be bringing one. Hopefully, I'll bring my big and fast one, but if it's broken, then it's broken. If you would like, I mean, these points go towards your grade. But again, if you once you submit it, you should get an email with like what you got right and wrong. So if you like retook it again, it would probably be pretty easy to get 100%. But yeah, I'm not telling you what to do, but you can do that.